Hi everyone. So in this next episode of our MIPS video series on physical AI, I'm going to be talking with Sam Grove, and we're going to be discussing the software and tools involved. Hi Sam, how are you?
I'm doing great. Thanks for having me today.
No problem. So physical AI implementation, there's going to be a lot of time pressures and potential risks involved. So maybe you could start off with looking at some of those and how they can be mitigated.
Yeah, that's right. So, if there's one trend that we've seen happen, decades and decades now in the semiconductor landscape is chips are getting more complex, more features are needed, lower power. There's lots of integration required, right? And with all these complex integrations and consolidations of technology into single chip designs,
Mhm.
you always wonder, how much work am I doing up front to ensure I'm hitting my power numbers, I'm hitting my performance numbers. We can go look at embedded software development surveys. For the last 10 years, they've all said the same thing. Achieving performance targets and debugging these systems is the most difficult part.
Sure.
That's where shifting left simulation technologies is so critical and important. At MIPS, our flagship product for aiding in this is called Atlas Explorer. And this is a hybrid simulation technology that actually enables you to look at your application workloads with microarchitectural performance details well before your SoCs are being taped out and manufactured. So you actually have a platform that your hardware architects, your software architects and engineers can all work on together to look at the
Mm.
details of things that catch every SoC at the end when it's too late and you're spinning another rev and
Yeah.
ultimately making compromises going to market.
Now that makes total sense because obviously, from a point of view, that if you get to a stage where you've got the actual silicon and then you find there's issues with it, then you're looking at having to respin all that and new
Yeah.
masks and God
And,
knows
and
what.
there's so much that we
Very
do as
complicated.
well, right? We do
Yeah,
spreadsheet math. We do so much math on sizing things roughly,
yeah,
kind of the swag finger in the air to get it about right. But, as these things get more complex and as you need to make a compromise in one area of the design versus the other to, meet all your requirements, why not
mm,
start looking at your software, before your hardware even exists, right? Now
yeah.
you can actually size it. You can actually put a real figure of merit or a number you care about in terms of, well, this is going to be in the market for 3 years, 5 years, 10 years, 20 years. What kind of room for expansion in the future do we need, right?
Yeah.
The software we ship with products when they come out, like the ecosystem, the world evolves very quickly. AI is a big piece of that in what we're living today. And we just don't know what the algorithms in 5 or 10 years are going to look like. And if you build
Mm,
something that's incompatible or was sized just right, or maybe even undersized to begin with, but you had to put it out, you find yourself in a position of weakness or on your heels. And we're trying to help companies, help designers make data driven design decisions based on the best information and knowledge they have today so that these platforms have a good future as well.
that makes sense as well because obviously, as you say, you want to make sure there's enough headroom there to allow you to take advantage of potentially sort of adding more sophistication to your design. But if you've not got the headroom there, you're not going to be able to do that. So this is giving you more visibility of basically what the implementation is going to look like in terms of how much silicon is going to take up, what sort of the different parameters are going to be, but also give you sort of the ability to sort of think, well, what next? What do you need to have in there that sort of
Yeah, that's right. So,
will
so,
allow
so
you to
much of
keep.
this work in state of the art technology as we know it today has been
Mm,
around virtual platforms, right? Functional representations of these systems. And those are critically important, especially as you hook them up into models of other parts of the system and build digital twins.
mm,
But the unique piece that we've kind of put together and where we're really kind of challenging state of the art and status quo is we actually have microarchitectural models of our processing platforms. And what that
mm,
means is you're actually looking at behaviors of interactions in the pipeline and in the microarchitecture, as well as the functional correctness of your code, right? And again, this is before your RTL is available, your system integration is done, before you're taping out your chip. So you actually have a huge advantage in terms of the amount of data and the insights about the workload's performance.
yeah.
In many cases, there are signals and things we're looking at that you can never, realize in silicon because they're too intrusive into the design. They might kill your area. They might kill your frequency, right? So having this technology, it's not just a shift left. It's not just something that we think about for pre-silicon design. This is the type of thing where even once you have silicon back, now you have the virtual representation and you have the physical representation. And you can take both of these forward throughout your product development lifecycle, right? The software development lifecycle that supports the products into the future. And you have, supervision into the machine, but then you also have the real thing that sits right next to it.
But that's interesting. So, before you said that, I would have thought of it just purely as the, the initial sort of stages of it. But obviously this has got whole life cycle sort of connotations as well. And so that there are advantages for that in terms of just, being able to have a better understanding of what is there. And obviously the more complex these systems get, the more value that's going to have. So, but it's not just the initial, sort of development, then it's the actual whole life cycle that you can.
If you think about it, right? You're in production, you're shipping this part. Now you got to do firmware updates. You got security vulnerabilities that pop up. You got a new model that needs to, get deployed on the device and run, the firmware update over the air, the IoT side of things for the last decade. We've been seeing, get into all these embedded products. A lot of these are weird shapes and sizes, awkward form factors because of the nature of the part of the, machine or the robot or the car that they fit into. What's easier? What do you think is easier, to deploy a simulator in cloud infrastructure and run and test your software, or doing this IT DevOps job of connecting all these weird hardware probes to custom boards, managing them remotely? There's definitely a place for that, but the more you can, use the simulation technology, use existing compute infrastructure that already exists, it just simplifies everybody's life, makes everybody more efficient, right? And ultimately, the less time we're all spending fighting infrastructure and fighting different, different bits of hardware and probes that may or may not fail, and running in and out of flash life because you've burnt it too much, and all those weird things, right? That's time you're taking away from actually building the product that you care about.
Yeah. And this is a more streamlined, more sort of, should we say, elegant approach where you don't need to. So there's a place for that, but obviously the more you can do in simulation, the more shift left you can sort of bring into the process, that the better, really. So,
that's exactly right.
Taking a software first approach, using shift left simulation type strategies as well. I guess that means then there's a lot less things that are potentially going to surprise you further down the line, because you've got that much better understanding and that better visibility of what's involved. Okay, so
that's exactly it. What we say is data-driven design decisions, right? If you have the data, you can make your choice very early, and it's more than, again, spreadsheet math and ballparks and theoretical maximums and some utilization percentage. You can get in there and see it, get in there and touch it, get in there and feel it.
Okay, so you mentioned Atlas Explorer, so maybe we could go into a bit more detail into how that sort of is helping customers, and maybe sort of maybe you could give an example of how the process would sort of all put together, how customers would use that then to.
Yeah, absolutely. So Atlas Explorer combines a bunch of technologies, right? It combines a functional instruction set simulator of MIPS RISC-V processor cores, combines the microarchitectural model of those same processor cores, and it then provides you with a user interface for exploring the source code mapping to the performance data and metrics that the execution or that workload had created. So if we think about it, it looks very much like software development that any developer would do, right? You have your source code, you have a part of it that you care about, you've profiled that whole workload, and it's like, look, I'm spending a bunch of time in this part of my code. Now, why, right? So you can see, well, my memory's been organized in a way that's not ideal, and every time I jump in and out of this loop, my cache is thrashing and I got to reload. And okay, so now we can start to work on data organization optimizations. Or you might find that, you're running an inner loop, and you're expecting to, get close to 2 instructions per cycle, and you're seeing 1.5. Well, you start to look at the disassembly, and it's like, well, maybe we had a performance optimization in the compiler that, didn't hoist some stuff out of loops because the code was written in a fairly generic way. Details like that, right? And so you're functionally making sure your code works. That's great, tick. Then you're starting to look at microarchitectural details about how that software ran on the machine. And that's where it gets super powerful, because whether you're trying to make trade-offs between code density and performance, max performance, right? Like these are different vectors that matter. Typically, you're going to have a deadline or a drop dead time you need to complete a task. And there's kind of two very simple vectors to think about. One, you unroll all the loops, you straight line all the code, you make it go as fast as absolutely possible. Well, that comes at a cost, again, to your ROM, your RAM, right, code size, and your data, right?
Yeah.
So now you might want to explore, okay, great, data memory dominates a lot of these designs. Maybe there's this happy medium that we can find in terms of how to retune the workload or how to use compiler flags and optimizations to get that right balance. So you are meeting your deadlines, but you're also, maybe saving some memory here or there.
Okay.
So once you, start to look at 4 or 5 of these key careabouts, these critical sections in code and programs that developers obsess over, you have this big data set, and with that data set, you can regex or use little clicky boxes to create these filters, and you take that and you just lock it up. So now you have a set of data that comes out of a run of this workload, and you have the metrics that you cared about that are all related to that kernel. You can take that and put it in CI/CD systems. So now you can send all your developers off to the races. They're building code, but you can very easily flag and check, hey, look, you checked in a piece of code. The report that was generated here regressed. You went from, 1.9 IPC to 1.2 IPC. Well, that's a big drop. We shouldn't do that, right? Or all of a sudden you're looking at, your cache miss rate or things like that, and it's just exploding. You're like, I wonder what happened. And so this is really about empowering developers with the tools they need to get the insight to the machines, just to make better decisions along the way. As a software engineer for nearly my entire career, testing becomes one of those things that's almost like your shield, right? If you think about it from like a infantry perspective, that's your front line. You got to build like this really robust kind of test suite or these interfaces on the boundaries that you care about, because as code comes in, whether it's from new developers joining the team, whether it's contributions to some open source software that's part of your application, right? If you don't have that visibility, you merge a lot of code in and like, boom, you're spending all your time trying to figure out what happened. Where did the regression come from? But, just little things like this, putting snippets of these things in the front and between the designs moving forward, it just gives everybody the autonomy to move very fast, but with a very high level of confidence that the pieces of the application on the hardware that they care about haven't regressed. And if they do, you catch it very early, right?
Yeah, that makes sense. So as you say that, obviously, you've got multiple engineering teams. They might be dispersed different parts of the world and so forth, all working on different elements of that, and then all of a sudden that's making something's come in and that's making a big dent on the performance or having some other impact. You want to have a good sort of insight into what's happening and what can be done, and also then if there are trade-offs in terms of time to market, you've got to get it out at a certain, how can you still do that without bumping up the memory reserves that are needed, or increasing the cost too much or anything like that. So I guess that's the thing is that, if you've got, as you said, that insight, then you can sort of, you can move a lot quicker through these sort of things. You're not sort of stuck at the end of a project realizing, okay, there's issues here that are really going to have a negative effect on the end product.
Yeah, that's exactly right. And if you think about it, right, standard SDK for a mildly complex microcontroller these days, we're hitting 2 million lines of code, right? Like, how many people actually understand that whole stack top to bottom, right? It's becoming too big, right? It's way too
Yeah.
big, right? So when you have these things, when you have these tools, and you can go start to put the filters on the parts of the, the critical paths that you care about that really make your product unique, or, meet your requirements for your customers and so on, that's really important. And so if we talk about it, right, 2.5 million, 2 million of lines of code for a microcontroller. Think about these embedded Linux distributions that are, out there on these kind of edge devices. Those are north of 2 billion lines of code, right? And so what I'm saying is the majority of software that's in these devices isn't even from the people who are building the products, right? This is a
No.
global activity, right? This is the world of software engineers that all contribute to these projects.
Yeah.
And we're pulling pieces together. We're, packaging them up. We're depending and building on top of, right? And at any point in time, you do have to maintain your dependencies. You do have to go look for CVEs and security vulnerabilities. You do have to make updates, right? And not every update is smaller and faster, right? Sometimes you had to put in a fix that was actually bigger and slower. And so now you need how do you actually identify that? How do you, cope with it? Figure out, was the generic fix that somebody else created that worked for them? Does it work for you? If it's in your critical path or your hot path, then maybe it doesn't. Maybe that's the kind of thing that you need to go spend a little extra time on yourself. And the question that you ask yourself is, how would you identify that in the first place? And then once you did identify it, what tools do you have to go fix it? And those are, a couple of the, key motivators that we think about when we're putting together these type of tools.
But as you say, the code's coming from so many different places, and they not all of them are even going to be inside your organization. They're going to be from different places outside of that. That obviously makes it, it's just impossible for one person to have complete knowledge of the whole thing. So you need these tools to give that visibility. Just a quick thing on that front as well. While you were saying that, is like, obviously, you want to make sure that your final implementation is performing well, and when there are software updates and all that it can still perform well, even when it's had patches and so forth put into it. But also, I guess, from a lot of the applications that we're talking about in physical AI are going to be, a lot of them are going to be safety critical. There's going to be elements of that. So obviously, from that point of view, if you've got lots of code coming in from different places, it's not just purely the performance. You want to have assurances that that it's still going to function correctly. There's not going to be issues with that. And on top of that, I guess, that it's not vulnerable to security breaches that might, have an impact as well. Yeah.
Yeah, no, that's exactly right. And that's one of the beauties of the RISC-V ISA is that, you look at it, whether it's the simplest microcontroller or the most complex application processor, the fundamentals of the design of the software interface to the hardware, it's the same, right? It's the same modes of execution. It's either present or it's not, right? It's the same memory protection schemes. It's how many do you have? And so when you think about it, right, one of the things that excites me the most about this is you don't have to go write, historically it's been write microcontroller firmware, and your microcontroller firmware looks very different than your embedded Linux application and software, right? But as these devices get more complex, right, as these systems do more and more and more, we're all just catching up to exactly where all these application processors have been for the last 15 to 20 years. Are we really going to go and rewrite all that software in a similar but different way to work on a microcontroller, or can we just leverage what's already there, right? In the same ways, like, how do you bring that in? How do you partition, your operating system in your supervisor modes, and making sure that your user modes have memory protections in place? So as you're partitioning your code and running it across these different threads or tasks, it's in these little containers. You don't get all that cross chatter. You don't have just a big open flat memory space that you're clobbering all over, right? You can actually partition your software quite cleanly. And again, whether you're running it on a low-end microcontroller or you're running it on a higher-end application core, the fundamentals and principles are all the same. The instruction set's still the same. The hardware blocks are still the same. It's just a matter of whether they're there or not. And that's where you get into your hypervisors, your RTOSes, or your operating systems that provide these system services for partitioning and isolation that it, ultimately helps you ship better products.
Okay, so that's cool. I mean, that's a lot to take in. But obviously, as you say, there's the fact that you're no longer having to, sort of think, oh, are we going to, we don't have to reinvent the wheel in terms of what's out there in terms of existing application processes. We can leverage what's existing there and write the code to sort of to deal with the MCU level sort of devices that are getting more sophisticated and so forth. So you hit on RISC-V, obviously having the open source architecture there and having that solidity of that and that sort of assurance that's that's something that your clients can rely on. But obviously that ecosystem has been developing over the years, and I guess sort of like over a decade now that's been sort of developing. I mean, MIPS has become part of that ecosystem in recent years, but is it in a position now you feel that it's with so many companies involved in it, so many different players sort of participating, is it in that sort of strong enough position now that is really going to be a big driver of the move for sort of edge AI and so forth?
Yeah, absolutely. Right. So when we think about that, my belief is, what makes software better? People using it, right? You can write the best piece of software in the world. You don't got a bunch of people using it. Like, yeah, who knows how good it really is? They're going to want to use it a bit differently. So overall, right, a few things here that, we think about when we look at the ecosystem. First is, given that the RISC-V ISA is open, you've immediately attracted a whole group, culture of engineers, enthusiasts and others who now have the ability to go explore, go prototype, go learn, go participate in a way that they never did before, right? Yeah, they did if they had a piece of, silicon or hardware, then they could go work on it. But, kind of bringing them much earlier into these engagements, into the development of the ISA itself, along with the software development, right? So as the ISA has grown and extends, one of the principles of it is, look, software and hardware implementation that go along with it, so we can all see, does this actually make sense? If I implemented this, does my compiler support it correctly? Can my software libraries make use of it? So the ecosystem's actually moved quite fast and far, just by the virtue of being open and available. In terms of how far along, for these physical AI, these, moderately embedded mid-range processors, like that's 15 plus years in this space. Like those are pretty well said and done, both open source communities, commercial, solutions. I mean, there's pretty significant market penetration there. Again, what makes any software better? More people using it, more silicon that we see in the market, more people that are going to be putting their hands on it, more eyes are on it. Just the better things get. Like that. I think that's the hard truth. There are ecosystems that RISC-V doesn't play so well in today. Like you just got to know that some of them are managed and controlled by large corporations, and until there's corporate alignment and interest to go pivot and bring RISC-V in there, like, it might be, there might be some rough edges, but all in all, the trends are in the right direction. It's, what do we say? There's very few bits of software you can pick up today that don't already support and run RISC-V. The question is it fully optimized for all the extensions or the flavor of chip that you have in front of you, right? That's the, what do they say? 80% of the work is 20% of the effort, and the last 20% of effort is 80% of the work, right? So there is that to go work on and do. But again, it's not a insurmountable challenge. We're working, building tools, bringing solutions to market like Atlas Explorer to really help shift that left and arm people with what they need in order to do some of that work even before the silicon comes.
Okay, so a couple of things there is, as you say, some ecosystems, that could be big, corporate politics is involved. Certain organizations are going to be controlling certain, but as you say, as a general, overall, then RISC-V is going to have this, sort of widespread appeal. And coming back to what you said, it makes sense because the more people you've got using it, the better the more robust it's going to be, because you've got more people scrutinizing it, and anything that does show up is then going to be dealt with pretty quickly. So you've got, it's sort of self-policing, I guess, because of the amount of people that are, sort of involved in it. So that the more momentum it gains, then the stronger it becomes, I guess. Yeah.
That's exactly right. I mean, that's fortunately or unfortunately, that tends to be how these things go. So,
So, but that puts MIPS in a strong position by being a big sort of proponent of this.
well, that's exactly
And
it, right? I mean, the more
yeah,
that we build these tools that give people these insights, they can do the work to optimize, to touch this again before their silicon is back and ready. So if you think about it, right, the silicon life cycle from, ideation of a processing platform to the subsystem design to tape out manufacturing, testing, and so on. Best case, that's a 2-year journey. Maybe it's 3, right? If you're doing okay. So 3 years of hardware, and then you get your software teams involved to go look at these things. Like, we're really trying to flip that upside down and say, no,
yeah.
like, your software team should be working with you there at day one. That's a 3-year head start. Like, think about how much software you can write in 3 years. Right?
As you
And
say,
that's
I
the
guess the
difference
traditional
between,
approach has always been to think of it like that, but now you've got to have a much more software first, much more. These guys are working in tandem with each other, and you're trying to fit, because otherwise you just, the time it's going to take up is just going to get longer and longer, because these things get more complex anyway, and the possible risks involved is just going to get higher and higher.
well,
So maybe one
and
last thing on
sometimes,
that front is
one key point on that.
based on the fact that,
I was gonna say just one
you
key
know,
point on that, right? Because
oh yeah,
the thing that's really important to understand is that if you get too far down when you find some of these issues in the design, like,
yeah,
there's nothing you can do about it, right?
yeah,
It's done, and now you're talking about tens of millions of dollars more to
yeah,
modify the chip, or we get it next time, which is another 3 years, right?
yeah.
So tens of millions of dollars, 3 more years, or let's just rethink how we work together.
And if you're a big corporation, that's one thing. That's still a lot of money and time and effort and human resource that's gone into that, that's wasted. But if you're a sort of smaller SME type company or a startup, you're pretty much toast then, I guess, because you're never going to get that opportunity to do that again. Because so to some extent, then it's a no brainer. You've got to think like this, or else you're going to be putting yourself in a lot of danger of
Yeah,
coming
that's
out.
it. I mean, I think these are the type of pivotal shifts. Those who embrace, they
Yeah,
become the leaders, right?
yeah,
Sometimes incumbents, they might get comfortable. They might, just be well in their ways, have their moats, do things the way they do them, and status quo is good enough.
yeah.
But, you know, give people the tools to do things a little bit differently and see what happens.
But some companies, like you say, maybe have an established way of doing this. They're comfortable doing that, but then they're putting themselves potentially in danger of becoming extinct because they've not adopted this quick enough. And then the companies that do embrace it quicker are going to get that edge, and they're going to be the ones that are driving the market, and sort of basically make a success of things as a result. Okay, so we touched on sort of where we are now in terms of basically how you can help the software development side of things, and how the implementations can be made more convenient and quicker and so forth. And I guess just looking ahead for the next sort of 10 years, I just guess those pressures, the time to market, the keeping the budgets down, keeping sort of being able to respond to potentially having to deal with updates and so forth quicker. Is everything just going to get more intense and more accelerated? Are there particular things that you see that are beyond that, or is it really just going to become the stakes get higher all the time in those
Well,
aspects?
yeah, if we go back to where we started, right?
Yeah,
The complexity and deep integration within these chips, right? For bill of materials reasons, cost of goods sold reasons, all of these things, right? It's pushing and creating that natural pressure to integrate more into the chip, right? The more that you integrate into the chip, the more software you have to go create, and these industries all have their own cadences, right? The refresh cycles, how quickly they
yeah,
move. on one hand doesn't do you a whole lot of good to build products faster than your customers can consume,
True.
right? But it only takes somebody to come along who is doing platform type thinking and is able to actually go rev hardware in backwards compatible ways or in incremental ways. And again, they're building better relationships with their end customers, right? They're building better relationships with their customers and their end users by being able to deliver continuous updates and improvements to their end products, right? So I think there are a lot of industries where physical AI goes into. I would consider many of those to historically be quite slow. But I think as we see some of this mechatronics, robotics, AI models and so on coming into those spaces, I think that's naturally going to speed up the refresh rate or the cycle in which they look to innovate on these platforms. And again, there's probably an open door for some, people who embrace, new methodologies to move fast and take customers on that ride.
But from what you're saying there, it's going to be the new sort of entrance into those markets that are forcing the other companies to sort of do stuff quick. It's not going to be driven so much by the customers; it's going to be driven by their competitors. And basically, if they don't, sort of move with the times, they're going to risk losing market share to a younger, more sort of, sort of more future thinking competitor, which might be a lot smaller, but has taken on board those sort of lessons a lot quicker than they have. So, okay, so that's an interesting point, because as you say, that's sort of going to, some of these markets where they're adopting some elements of physical AI, but they probably aren't really, sort of used to the approaches we're talking about, they could potentially lose out because they haven't sort of moved quick enough with the times. Okay, so
and if you think about it too, right? There's today it might be a piece of silicon that has a new compute capability that moves the needle. It might be a new foundational model or a new network topology or graph of a model for running some sort of inference on the edge to make these decisions or control these motors or move a conveyor belt in a production facility, right? And again, it's going to be, if your refresh cycles in those markets are 10 or 20 years, like the compute and chips we built 10 years ago, do not run these newer hardware or these newer software stacks very well, right? So the whole thing will move faster, like no question about that, right? And some of it will be driven by hardware compute capabilities. Some of it will be driven by a new architecture or a new model architecture that comes out, and that will drive the new compute capabilities, and that will push into these refresh cycles in industry.
Okay, but the stakes are gonna keep on getting raised, and things are gonna be quicker moving, and those who don't really sort of adopt this approach early enough might well not be there for that much longer. Okay, finally, from a MIPS point of view, what do you feel you have to do now in supporting your customers and bringing in new customers? What would you say were the key things that, as a company, you need to be doing in the next few years to get a stronger position in the market?
Yeah, great question, right? So MIPS has had a long history in this industry, ups and downs along the way. We're back on one of those ups, and there's lots of things, right? This is a relationship industry. This is a partnership industry. It's not vendor pass something over the fence, customer take it and go, right? There's lots of collaboration that needs to happen all across the stack. That happens, in B2B settings. That happens in open source communities and consortiums. And so, if I look at what's really important, for MIPS the next couple of years, it's getting back out there, making sure people know what we're doing, seeing us. We've started actively contributing to lots of open source projects again this last year, and so it's kind of that, like, hey, we're back, here we are. It's as much as we're doing work we could have done many years ago with the support for some of the old MIPS ISA cores that are still in production, still shipping in great volumes. It's also all of our newer RISC-V platform processors, and so you'll see us both within those communities, contributing and collaborating. You'll see us in RISC-V International and the working groups, technical steering committees, and so on, working there. You'll see us with industry consortiums, collaborating with other vendors that are looking at application-specific markets and domains. And you'll see us, all across the world in B2B relationships with our customers, again, championing these industry best practices, and not just talking about it, saying that we should do it, but actually delivering and providing tools to do it together. Right? It's lead by example. It's not just talk. Right?
But that's great, because as you say, you need to be visible. You need to be out there, whether that's in the RISC-V International working groups, whether that's in consortia that are doing different projects. You just got to be seen to be a big part of that sort of overall community that's built up around RISC-V, and then that obviously that gives you sort of that recognition throughout the industry that you're a major player. And I guess that from there, that's sort of and so it's not just about developing new IP or developing new tools. It's also about being proactive with what's going on in the community then. Yeah.
Yep. That's exactly right. Excellent. Right.
Okay. Well, look, Sam, it's been an absolute pleasure speaking to you. Thank you very much. It's been really interesting, and I hope we get a chance to speak again in the future.
Yep. Likewise. Very nice to chat.
Thank you for your time. Cheers.